nth roots of complex numbers. So what does that mean? Well, we're going to be looking at finding, say, like a square root or a cube root of a complex number and how to do that. So, example, find the principal square root of 1 plus root 3i. And when I'm talking about the principal square root, this is just giving us information about kind of which root we're talking about. So when you see that, and we'll talk about what that looks like, but just as a reminder, if I have something like x squared equals 3, and this is just, of course, for real numbers, and I want to solve that, I get x equals plus or minus root 3, so I get two values, and so from here, root 3 is the principal square root. So it's a little bit different with talking about square roots or principal square roots with complex numbers, but we'll have a way to do that. Okay, so we'll kind of hang on to this idea of which one is the principal square root for a second, but just finding the square root of a complex number, what is that going to mean? Well, our steps are going to be as follows. So first we're going to put into polar form. We're going to put this number into polar form. Then we're going to raise it to the 1/2 power, because I know that this fractional or rational exponent of 1/2 is the same as taking the square root. So we'll do that. And then put that new number back into rectangular form. Sometimes you'll hear that as standard form. Rectangular form. Okay, so let's do step 1. So first I'm going to say, let z equal 1 plus root 3i. Sometimes it's helpful to have a name for your number. Okay, so if I have that and I want to put it into polar form, usually what I like to do first is just go ahead and kind of plot about where that would be. So here's my number z. And again, this is like my imaginary axis for plotting a complex number. But the important part that I'm trying to get out of here is r is the length of that segment here. And of course, my angle theta. So I want to find both of those. So r squared, I know, is just take the real component and the imaginary component, a and b. So those are still real numbers, and just square them. I get r squared equals 1 plus 3. So r squared is 4, so r would just be 2. And how do I pick between 2 and negative 2? I do so because r is just a line segment and I need it to be positive. Okay, so how about my theta? Well, tangent of theta I know is just vertical over horizontal, so root 3 over 1. And so tan inverse of root 3, that's a nice unit circle number. So this is just pi over 3. And that is in quadrant 1, so I'm good. So, but why not say negative 5 pi over 3 or something like that, right? Like, why wouldn't I pick that angle? Well, for the principal square root, so now we finally get back to this, theta needs to be in the set negative pi to pi. So we just check, is pi over 3 inside between negative pi and pi? Yes, so we get to keep that. So here we say theta is pi over 3. So if it's asking for the principal square root, you just go, I must use the angle theta. So we don't want to use the one where I'd be going backwards. It's coterminal angle. Okay, so good. If it asks for any square root, then you could pick any angle. Okay, so I have r and theta. I put it into polar form. Okay, almost done there. So I'm going to have z equals 2 times e to the I times pi over 3. Okay, so 2 says raise it to the 1/2 power. This is just me. This first step is just me saying, hey, here's the same. I have the same number. I haven't done anything to it yet. But it says, hey, find its square root. And you say, find the square root. Well, square rooting something is the same as raising it to the 1/2 power. So if I raise both sides to the 1/2 power, this is just saying z to the 1/2, its square root, is equal to 2 times e to the I pi over 3 to the 1/2. Well, what's that going to look like? Well, we know that if I have, say, a times b to the m, this is the same as a to the m times b to the m. Just means we have to raise each thing to that power. So this becomes 2 to the 1/2 times e to the I pi over 3 to the 1/2. So it's kind of like distributing. 2 to the 1/2, that's just root 2. Now, when I have, let's say, do another example, a to the m all to the n, say this becomes a to the m times n. Just means the exponents multiply. So this gives me e to the I times pi over 3 times 1/2. Well, that just gives me pi over 6. Okay, so now this is z to the 1/2. Great, except this is in polar form, right? This is the polar form of my square root. So step 3 up here said, okay, once you have that, put the new number, so this is my new number, back into rectangular form. Great, let's do that. So how do I do that? Well, first I usually have to go by way of trigonometric form. So z equals root 2 is my r, all times the quantity, cosine of pi over 6, plus I sine of pi over 6. Okay? This gives me root 2. Cosine pi over 6 is root 3 over 2, plus I sine of pi over 6 is just 1/2. Okay? And then I'm going to multiply that root 2 in. I get root 6 over 2 plus root 2 over 2i. Now, let's see, what did I mess up here? Well, I wrote this as z, but this is still z to the 1/2, right? Because I'm saying, hey, I found this, the square root. So I want to be really careful that, what I first said was this is z, and now when I'm taking the square root, it should be a z to the 1/2. Now, one way to check your work, so how could I check this? Well, this is the square root. When I multiply it by itself, it should get me my original number back. So let's check it. So if I do root 6 over 2 plus root 2 over 2i, and I multiply that by itself, okay, I'm expecting it to get me back z, my original number. Okay, let's see if that happens. So the first two things multiplied together, root 6 times root 6 is 6, 2 times 2 is 4. So all I'm doing is just saying, let's do the first things together. And that gives me this number here, okay? Plus the outer things. So root 6 times root 2 is root 12. So that's root 12 over 4i plus, all right, well, those inner parts are going to give me the same thing. So another root 12i over 4, right? And then my last two things are going to be, got to be careful here, root 2 times root 2 is 2, I times I is -1, and then 2 times 2 is 4. Okay, so hopefully this should all pan out to give me my original number z. Okay, let's try it. So 6 over 4, that's just 3/2. Let's see, root 12i, root 12i. So now I have two of those plus 2 root 12i over 4. So all I said was if I add these together, there's two of them. So now I have 2 root 12i over 4. Plus, this is just -1/2. Okay, so let's see. 3/2 minus 1/2, of course, that's just 1. And then let's see what happens over here. I get divide out a 2, leaves a 1. Divide out a 2, leaves a 2. And then what's root 12? Let's see. Root 12, right? I'm still on this part here. Root 12 is just 2 root 3. Okay, so this leaves me with 2 root 3i for the numerator. And then there's still a 2 in the denominator. So that gives me 1 plus root 3i. So I am expecting, right, if this is z to the 1/2 and this is z to the 1/2, then multiply them together, right, I'm expecting this to be the value of z. So let's go up and check. Yes, z was 1 plus root 3i. So I've done it.